this is a practice session for our final exam. Now, I tried to choose questions that I thought would be most important to General Chemistry 2 and or things that I thought you might have forgotten and needed to be reminded of. But this is not exhaustive. This is just kind of the highlights that I really wanted to make sure that you got. I'd say if you get all of the things in this review session, you thoroughly understand them and know how to do them, that's probably 80 to 90% of the exam. So just kind of make sure you understand the concepts, not just memorize the questions, obviously, because I will be mixing them up. And I'm not just copying and pasting from this exam. I'm going and pulling from all of your past exams that you've had in this class. So go look at all of them and review all of them. All right, so first off, a reminder, here is our time of our final exam, but remember you may take it early, Monday, Tuesday, or Wednesday of that week, and there is a sign-up sheet that I'll be passing around in class, but besides that, take a look at all of this material, decide when you want to take your final, and if you can't take it early, you don't want to take it early, take it at this time. Okay, so if we scroll down to our first question, subatomic particles. So remember, the atomic number is the number of protons. So if we look up strontium, it has a little SR and a 38 above it. That is our number of protons. If it is written like this, then this number here is your mass. So if we take 88 minus 38, that's going to give us 50, and that equals the number of neutrons in our atom. So my answer there is 50. Same thing on chlorine. This mass here is irrelevant because if you change the number of protons of a compound, you are changing what element you are. So this would just be 17, chlorine's atomic number. How many sig figs are in each of the following numbers? Now remember, any trailing zeros are not significant unless there is a decimal. There is no decimal here, so I count them. 1, 2, 3, 4, 5, 6. There would be sig figs here. Middle zeros are always significant. Here, there is a decimal. Decimal means trailing zeros are significant, so there are 3 sig figs in this number. Same thing here, there's a decimal, so all of those digits are significant. This next one, when we convert this to scientific notation, we move it 1, 2, 3 over to the right, making it 3.050 times 10 to the minus 3. That zero is significant because it is a trailing zero after a decimal, so therefore I must include it in scientific notation. Now to naming, your guys' bane of your existence, I often find. So remember, if it has prefixes like this, it is a covalent compound. If it does not, it is ionic and or it is a polyatomic. So in this case, if we have iodine, iodine is I. Hepta is 7, so there are 7 fluorines. So that is my chemical formula. Calcium oxide, there is no prefix, so therefore that must be ionic. So I look up calcium in the periodic table, it's in group 2, so it forms 2 plus ions. Oxygen is in group 6, so therefore it forms 2 minus ions. I heard something the other day that made me laugh. They said swap and drop, and it just made me laugh because you swap them and you drop them, and then whenever you go the other direction, you unswap and drop, and I'd never heard that before. So this one would be, you would think it would be Ca2O2, but then you have to reduce it. Okay, so you always want to reduce. So that makes this one CaO. All right, now let's look at cobalt. So I'm not going to tell you the name because we got to figure that out. All right, so cobalt and chlorine, and there's 3 of them. And if cobalt is a metal and chlorine is a nonmetal, which is a true statement, we need to bring the 3 up, bring the 1 up. That makes it CO3 plus, chlorine minus. Is that chlorine's true charge? Absolutely, so I don't need to do anything with it. Making this be cobalt. 3, remember if it is a type 2 ion, which cobalt is located within the D group, the D block, then it is a type 2, and we need to give it Roman numerals. So cobalt 2 chloride, not chlorine. Naming those prefixes and those suffixes do actually matter. All right, now on to a density question. The density of a subject is determined by water displacement. Okay, so if we have a final volume of 22.58 milliliters, an initial volume of 16.20 milliliters, and we subtract them, that will give us 6.38 milliliters, and that is the amount of volume that was displaced by the object. If I know its density then, and I know its volume, and I can write that over here. Volume is 6.38 milliliters. Density is 3.75 grams per milliliter. Also paying attention to sig figs, meaning this was a shared common denominator place value, whatever you want to call it. Place value is probably the best word. That means that that is my significant digit there. Okay, so now I go to my formula for density. Density equals mass over volume, which means mass equals density times volume. So my mass equals density 3.75 grams per milliliter times my volume 6.38 milliliters. I have the same units, so my units are going to cancel, leaving me with a mass and only 3 sig figs to report of 23.9 grams. And that's my final answer. All right, balancing, everybody's favorite. So remember, just take all the elements, put them down the middle, decide how many are on each side. So for instance, on the left side, there are 2 nitrogens, there are 8 hydrogens, because remember you have to multiply those 2 together, 1 carbon, and 3 oxygens. Now on the right side, how many do we have? I have 1 carbon, oxygen is in 2 places, so I have a total of 3 of those. Nitrogen, there's only 1 on this side, and hydrogen, there are 3 in there and 2 here, so a total of 5. All right, so let's start changing things. If we put a 2 here, that's going to make this go to 2. It's going to make there be 6 hydrogens plus 2 makes there be 8. And wow, that was way too easy. I'm totally going to need to choose a harder one for your exam. Okay, so practice that balancing there. Okay, so now we're going to do a limiting reagent problem. These things are so important because they remind you about all of those molar conversions, which you guys have gotten so good at and hopefully have not forgotten. So first off, do a quick check. Is it balanced? 4 lithiums, 4 lithiums. Yep, that thing's balanced. Now I need to decide which one's my limiting reagent. How do I know that? It's because if you got so many grams of one reactant and so many grams of another reactant, one of them is going to be limiting, one of them is going to be in excess. In order to figure out how much product you truthfully have, you have to determine first which one is the limiting reagent. Okay, so I'm going to cheat. I'm going to come down here and figure out what I'm actually getting asked. In this case, what mass of lead 4 sulfate. So I'm caring about this molecule here. So my strategy that I'm going to use while working this problem is I'm going to turn both of these into this one. Okay. And I mean, I can stop at moles. And then for my last final part B, I can turn it into grams. So I'm going to convert from grams to moles to moles, and see which one is smaller. Okay. So what do? We have 4.250 grams of my lead 4 chloride, which is PbCl4. And then I also have 2.165 grams of my lithium sulfate. I need to first convert from grams to moles. Why do I need to do this? Because I need to get it into moles so I can use my molar ratio to convert both of them into my product. Okay, so how do I convert from grams to moles? I use my molar mass. I'm cheating. I have pre-figured this out. That way you guys aren't waiting forever for me to calculate this in a video. I fully expect you to be good at calculating molar mass by this point in your education, so I'm not going to cover that in this video. And so that is 349.012 grams of lead 4 chloride. And this is 109.943 grams of my lithium sulfate. Okay, but now I have moles, but I can't just find the answer here and put equals because that would give me moles of lead 4 chloride and lithium sulfate. I need to get them in the same unit. So in order to do that, I need to convert both of them now into my lead, lead 4 sulfate. Okay, so how do I do that? I look at my coefficient. So this is 1 to 1. So that is 1 mole of my lead 4 chloride for every 1 mole of my product. And then same thing here, except for now I have a 2. So I'm 2 moles of lithium 2 sulfate, or sorry, not lithium 2, just lithium sulfate for every 1 mole of lead 4 sulfate. Okay, and that's going to give me my answer. So I plug all that into my calculator and I get 0.012177 moles of my lead for sulfate, and I get 0.009846 moles. And so now I need to look at these two numbers and say which number is smaller, and that means that this number here is smaller. And so since that number is smaller, that makes this be my limiting reagent. So lithium 2 sulfate is my limiting reagent. Or sorry, lithium. I don't know why I keep saying lithium 2. It's just lithium sulfate. Lithium is not a type 2 ion, so I do not need my 2 there. Okay. So I've now figured out which one's my limiting reagent, which means my excess reagent, of course, is going to be on my lead 4 chloride. Okay, so now what I can do is I can take this value here and convert that into my mass of my product. So I have 0.009846, and that is moles of my lead 4 sulfate. I need to convert that into grams, and so once again I use my molar mass, and I have pre-calculated that to be 399.322 grams. That's going to give me 3.932 grams of my product. Woohoo! All right, so there's my answer. Now I did do 4 sig figs because I have 4 sig figs in each of my initial 2 numbers, so that's why I chose 4 sig figs at that point. Okay, so now the final question is, if you actually produce, so this is your experimental yield. This is my experimental yield. So I need to take my actual yield, which is how much I actually got, okay, my experimental yield, and I need to divide that by how much I could have made in theory, okay? Now the main thing here is to make sure your units are the exact same, and mine are, and so I'm good to just plug them in here. And then you also can't forget that you have to multiply it by 100 to get it into units of percentage. And that leaves me with 70.93%. Okay. Remember, percent yield is different than percent error. Percent error, you do the subtraction on top. Percent yield is just one over the other. And that's typically used in organic chemistry and or any reaction where you're producing a product, which is what we are doing. So that's a limiting reagent problem. I could also go through and ask you, how much of my excess reagent is left over. Okay, so all you gotta do then is just do a little subtraction, okay, and figure out how much is remaining from there. So just doing all those conversions. All right, so now more questions. This one, number 9, is looking at molarity. So that's your solution. So remember, molarity is moles per liter, and oh man, are we gonna use that in Gen Chem too. Okay, so that is huge. No, as soon as you have a big M, that just stands for moles per liter. You need to be doing that like it's nothing, like you were born converting those conversions. Okay, so where do we want to start? First, we've got how many grams, so we're trying to figure out how many grams we've got. So remember, if you take molarity and you multiply it by your volume, that's going to give you moles, okay, because moles per liter times your liter is going to give you moles. So what we can do is we can take our molarity, which is 1.50 molar, which is the same thing as moles per liter, and we can multiply by our volume. But notice here, in order for these to cancel, they have to both be in liters. So I need to convert 25 milliliters to liters. You guys all should know by now that that's 0.0250 liters. It would be like 00, but whatever. Doesn't matter. Liters. Okay? Then I'm trying to find grams. So how about I just also, at the same step, convert from moles to grams? So 1 mole of sodium phosphate. You actually don't have to know what the formula is for sodium phosphate to answer this question, but you do need it for this step. Okay, so for the first step, how many moles you would need, you don't need it. But for this step, you have to know that phosphate is PO4 3-, which makes this sodium phosphate in a 3PO4. Okay, so then its molar mass is 163.94 grams. I strongly suggest that you calculate that amount right there. So what I think I'm going to do is I will make an envelope and I will put all the formulas that you might need there that I might have given you if you walked up to the front and said, hey, what's this? Take off points. I think I'll put them all in an envelope. And if you need it, you got to take all or nothing, okay? I want you to know those ionic structures. So many of you guys don't know them. I need you to know them for the final. So I'll make it so if you open the envelope, you lose 5 points or 10 points or something like that. So you're going to have to decide whether or not it's worth it to you to open up the envelope to get all of those values. And what it'll be is just however many I put in there. It'll be -1 for each one I put inside the envelope. I'll tell you what that is as soon as I, make it. Okay. But I want you to know those ionic structures, those polyatomics. Know them. Okay. So plug all that into your calculator and you get 6.15 grams of sodium phosphate. And we are done. So this is an example of a molarity problem, a molarity times volume, and actually asking how much would you need. And so these are very realistic, very, happens to me all the time when I go into lab type questions. Okay, next we have a titration. Titrations are going to be all over Gen Chem 2. So this one is a titration problem. So it says we're trying to find the molarity of an acetic acid solution. So this is something you guys did in lab. So you guys titrated vinegar using sodium hydroxide and your sample turned pink with KHP. Or no, you didn't use KHP. Excuse me, you guys used phenolphthalein. So you guys were doing a little standardization. The main thing is at equivalence point, moles of acid equals moles of base. And if that is true, which it is at your equivalence point, then you're able to just convert one into the other. So moles of acid equals moles of base at your equivalence point. Okay, so what do we know? It was titrated with sodium hydroxide. So first we can use that volume and that molarity to convert from molarity into moles of sodium hydroxide. So we have 1.00 moles, which is molar, which is moles per liter, times my volume, 0.01547 liters, convert it to liters so my units cancel, and that is going to give me 0.01547 moles of base, NaOH. And remember what we just said right here, they are equal, so this equals 0.01547 moles of acetic acid, which is CH3COOH. Okay. And so now I know how many moles of acetic acid I have. Well, if I know I have 50 milliliters of it and I'm trying to find the molarity, that's what I'm solving for, I can take 0.01547 moles of acetic acid and I can divide that by the total volume that was in my solution. Once again, converting that into liters because I want molarity. And so when I do that math, I end up with 0.309 molars, 3 sig figs because of my molarity there only has 3 sig figs. And I'm fixing my units. And I'm done. Okay, so this is an example of a titration problem. The main thing with the titration problem is knowing that at equivalence point, moles of acid equals moles of base. If you wanted to, you could write a titration. You guys remember doing that? So sodium hydroxide plus CH3COOH. What's going to be produced? I'm getting a single arrow because sodium hydroxide is a strong acid. I'm going to get a salt and water. But how do I get that? Well, if it's a strong base, remember it's going to donate hydroxide. What's it going to donate it to? Here, we got another hydrogen here, so it's going to strip that off. So we've got H2O plus the things left behind are sodium and acetate. And you could write those together or you could write them separately. And so here is my salt. That's a really weird little line, but salt. Okay, so let's move on. Next, number 11, we have another limiting reagent problem. Can you tell these are kind of important, mainly because of the concepts that they teach you? So first things first, we need to write a balanced chemical equation, which means you have to know how to do those polyatomics. So if we got iron 2, that's Fe2. Nitrate is NO3 minus, combines with ammonium, and the IUM means it is a positive species, and then carbonate, CO3, 2 minus. After the reaction is completed, how many grams of precipitate could theoretically be produced? So we're supposed to identify the limiting reagent and the excess reagent. So in order to figure out how many grams of precipitate, we first have to figure out what is the precipitate. So let's combine them. Fe, my 2 comes down. So NO3, my 2 comes down, my 1 comes down, which makes it iron 2 nitrate like that. Plus, we've got ammonium, NH4 plus, and then my carbonate, my 2 comes down, and then this becomes CO3. Okay, so Are these aqueous? Absolutely. How do I know that? Most ammonia species are soluble, most nitrate species are soluble, so both of them together are definitely going to be soluble. So now what do we do? Remember, this is where you combine your anions with the cation of the opposite one, so you charge them like that, which makes this be Fe2 is combining with CO3 2 minus, which means we have FeCO3 is one species, and the other one is going to be our ammonia in H4, and that's plus, combining with nitrate, which was also minus. So both of those cancel out and have a single charge. Okay, remember we said ammonia and nitrates are soluble, which leaves this one to be the precipitate. Most carbonate species, especially with type 2 metals, are going to be solids. So we have now figured out our precipitate. That's the important part. Before we proceed, we should balance this. So what do I need to do to balance it? I have 2 ammonias and 2 nitrates on the left, so I need there to be 2 on the right. So now I am nice and balanced. So first step, I know I need to convert both into iron carbonate, iron carbonate. So I'm going to take both of my reagents and I'm going to react them together and determine how much iron carbonate could be produced by each of them. So to do that, I'm going to start out with nitrate. So I have 1.25 molar of my nitrate. I'm going to multiply that by my volume in order to figure out how many moles I have. And that would give me moles of, because remember, molarity can be written as moles per liter. So I'll write it like that so you can see it. So my liters are going to cancel. I'm left with moles. So now I need to cancel out my moles. So for every 1 mole of iron nitrate, I have my molar mass, which is, wait, I don't have to do that. Why do I not have to do that? I don't have to do that because I'm trying to get from moles of this species to moles of this species. So I can just immediately convert it without going to grams because I already got in moles. Moles is the goal, right? To moles of iron carbonate. Okay, then I need to go into grams. So meaning 1 mole of my iron carbonate has a mass of 115.854 grams of iron carbonate, and that's going to give me a total mass of 3.939 grams. That's not the right sig fix, but we'll fix those later, of FeCO3. Okay, I just kept extra sig figs in case, my limiting reagent problem is close. So that's how many grams I could produce from 27.20 milliliters of my 1.25 molar solution. Now I need to use my other numbers, which are here and here, and I need to do the same process in order to get me all the way to grams of iron carbonate. So I've got 0.756 moles of ammonium carbonate. And that's per liter times my volume. Converting it to liters, of course, and then I need to convert it all the way over to my product. And this was too easy of a problem because they're both 1-to-1. I don't really think I should have it be 1-to-1 for you guys, but we'll see what happens. And then I need to convert it to grams of iron carbonate. So same molar mass as before. And that equals 4.6096 grams of my iron carbonate, which means that, which one's my excess reagent? Right here. And which one's my limiting reagent? This one. Okay, so I would come up here and I would put FeNO3 2 there. And I would put my other one in H4 times 2 CO3 on the other one. Okay, so I've now figured out my limiting reagent and my excess reagent. And my final question is how many grams of precipitate can I have? So I need to fix my sig figs. And my final answer is 3.94 grams of iron carbonate. That's my final answer because that is my solid. Ooh, man, we're rolling now. Let's keep going. Now we're in the world of gas laws, everybody's favorite thing. So remember, for these, you just got to make sure your units are all according to what they should be, and then you use whatever equation makes sense. So we have a sample of nitrogen gas. So my temperature is 298 Kelvin. I have a pressure equal to 745 torr. We know we need to convert that to atmosphere, so I'm going to do that. How did I do that? Remember, we got the list of conversions on the front couple pages, but 760 torr is equal to 1 atmosphere, so you can just convert it. Okay, so then it says we have a volume of 37.42 liters. Man, that's a lot. Okay. And then it's saying what volume, which tells me this is V1 and V2 is what I'm trying to find. Okay. If the pressure is increased, so pressure goes to 894 torr, which is equal to, if we do that conversion, that is 1.176 atmospheres. Okay. And it's at a constant temperature. So T2 is constant. So T1 equals 22, which is 298 Kelvin, which means they're essentially going to cancel out. Okay. So if I have my combined gas law, P1 V1 over T1 equals P1 V1 P2 V2 over T2. My T's are constant, so they're going away. So I'm left with P1 V1 equals P2 V2. And I need to solve for what I'm looking for, which is V2. So P1 V1 over V2 equals P2. And now I can come over here and I can solve. So, whoops, I did the wrong direction. I'm looking for V2. So that means this one should be P2. Whoops. P2 and this one's V2. So V2 equals pressure 1, 0.98 atmospheres times V1, which is 37.42 liters, divide by P2, which is 1.176 atmospheres. V2 therefore equals 31.2 liters. And if we have increased our pressure, does that make sense that we would decrease our volume? Yes, because those two are inversely proportional. All right, so there's a gas law problem. There's lots of different gas law problems you can be asked. Okay, now on to a specific heat or a heat capacity problem. We have benzene, and then it says our specific heat capacity, so that is S. S equals 1.74, and that's joules per gram degrees Celsius. If 16.7 kilojoules of energy, so that's my Q, that's my heat. So I've got 16.7 kilojoules is absorbed by, we've got our moles, N equals 2.88 moles, okay, at 20 degrees Celsius. So T initial, and that says that's the initial temperature because the other one is final. So T initial is 20.0 degrees Celsius. And what I'm trying to find is T final. Okay, so let's ask ourselves first, how do our units look? Well, we've got Celsius and we got Celsius. So Celsius is fine. We've got joules and we got kilojoules. So I need to convert one to the other. Since I have more room, I'm just going to do it right here. So meaning we've got 1,000, did it the wrong direction. We got 1,000 joules over 1 kilojoule. So that's going to give me 16,700 joules. So now we've got joules matching. What's the last step? Joules, grams, and moles. And so those do not match. So I need to convert my moles to grams. How do I do that? I have my molecular weight. So that means I can convert 1 mole of C6H6 into grams using the molar mass. And it is 78.11 grams. And that gives me a mass of 224.97 grams. All right, what equation do I use? Q equals SM delta T. Remember, delta T is the same thing as T final minus T initial. And what I'm solving for is T final. So I need to get that by itself. So the first thing I do is divide both sides by SM. So Q over SM equals T final minus T initial. I then can add T initial to both sides, canceling it out there. And that makes it be T final equals T initial plus Q over SM. And now I can come over here and put my final answers in here. So T final equals T initial, which is 20 degrees Celsius, plus Q, which is 16700 joules, over S. S is 1.74 joules per gram degrees Celsius. My joules are going to cancel. And then I multiply that by my grams, which is 224.97. And that's grams. So my grams are canceling. It's going to end up with degrees Celsius all over here because 1 over Celsius equals Celsius. And so that's going to leave me as Celsius plus Celsius. Put all of that into your calculator and you should get a T final equal to 62.7 degrees Celsius. Okay, and that is the right sig figs. We're looking at place values and that's the tenths place. And you're going to get more than the tenths place over here. And so you're going to round it to that tenths place. All right, this is a specific key problem. Q equals SM delta T. All right, now we're getting into the stuff that is probably most familiar to you because it is most recent. So this is all the stuff on the most recent exam. Orbital electron shorthand configurations for iodine. So I chose a really big one just for you to practice. Don't you just love it? Okay, so iodine has 53 electrons. So man, we got to go far. Iodine, it should end up, if I look at my periodic table, it is in the 5th row. It is in the P group. So I need to end with 5P. So 5P is my last one. So I'm going to go 1S, 2S, 2P, then 3S, then 4, wait, what did I just do? 3P, excuse me, and then 4S, and then 3D, and then 4P, and then 5S, and then 4D, and then 5P. And you fill in all my electrons and just count. So I'm at 20, and of course I'm not actually filling them up, down, I'm filling all the other ones over first. So that'd be 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53. Boom. And it ended up exactly where I thought it should. Happy day. And now I need to do the electron configuration. So remember, this is just an active copying. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. Boom. And you're done. Then I go look at my periodic table. The first noble gas before iodine is krypton. So that would be Kr, 5s2, 4d10, 5p5. Okay. Fantastic. And now we're going on to my quantum numbers. Germanium, I looked that up, and that is 32 electrons. And it is in the 1, 2, 3, 4. 4p is where that last electron is going to be located at. So it is in a 4p shell. 1, 2, 3. There are 3 orbitals within a p. Middle one is 0, -1, +1. So if germanium has 2 electrons in this, it should go 1, 2, which means we've got N, L, M sub L, M sub S. N is going to be 4 because of 4p. L is going to be +1. M sub L is going to be my 0. And then my M sub S is my +1/2 spin. Okay. Now, John Lewis structure for potassium fluoride. I don't have any prefixes, so this is ionic. Woo-hoo! Potassium is Kk. It has a +1 charge. Fluorine is, of course, -1. Y'all know that by now. And there is my Lewis structure. If it would have been like K2F or something, then the 2's would go out here, 3, etc. Okay, but obviously we know it is not that because I need to drop those plus and minus charges, giving me KF. Okay, last but not least, reminding us of Lewis structures, the fancy covalent kind. All right, so once again, do you know your names? Ammonia, NH3. Tellurium tetrafluoride. So we got a tetra there. So we got TeF4. Carbon dioxide, CO2. Ammonia, we've got 1 nitrogen. That's got 5 electrons. Hydrogen, there's 3 of them, and there's 1 in each one. So we have a total of 8 electrons. Tellurium, if I look it up on the periodic table, it has 6. Fluorine, 7 times 4. That gives me 28 plus 6 is 34 electrons. Carbon dioxide, carbon has 4, oxygen has 6, times 2, 12 plus 4 is 16 electrons. So now I can go draw all of these. Least electronegative in the middle, but good old hydrogen cannot be in the middle, so it has to be like that. I've just drawn 6 electrons, which means I need to draw an extra 2 in order to hit 8. There's my structure. Tellurium, if I draw it with all of my fluorines, I'm going to end up with 32 electrons. How do I know that? 8 times 4 is 32. If you can get really good at these multiples of 8, you'll get there a lot quicker. So if I have 32, 32 is less than 34. Where do my extra electrons go? Right in the middle. Carbon dioxide, C to O. But remember, carbon wants to have 4. So I need 4 bonds coming off of it, which gives me this structure. Is that the right number of electrons? Absolutely. 8 times 2 is 16. Now, bond dipoles. Remember, you draw the least electronegative gets the positive side, the most gets the arrowhead. So hydrogen, less electronegative than nitrogen, so it goes toward that way. Fluorine is the most electronegative atom, so it gets to pull it toward it. And then carbon, oxygen. Oxygen is more electronegative than carbon. So there's my bond dipoles. Now, molecular geometry, go look. And remember, you should already have these memorized. So you've got trigonal. You've got tetrahedral, you've got seesaw, trigonal, bipyramidal, and linear, last but not least. Which means, are any of these symmetric? Well, thanks to all those electron pairs, the first 2 are not. So therefore, this one is polar, this one is polar, and this last one is symmetric. So it is non-polar. Which means if you had to draw a molecular orbital, this one would be going something like that, straight up through to the, I guess I should draw it like this, straight up to the electron pair. And then this one's a little hard because there's 4 fluorines pulling down, so it would probably actually pull down toward all the fluorines, because that one is our little seesaw, if you will. Okay, so that one's kind of fun, because you've got 2 fluorines pulling down, 1 pulling up. These 2 fluorines here and here would be canceling each other out. So that one's tough as to which direction it would go, but it's polar. That's all that matters. Okay, and then here, there is no molecular dipole to be drawn, so it is not polar. And with that, we have covered a lot. But you remember everything we've covered. Even look at all these charts. What did all of these tell you? We go back and look through and be like, oh, I do remember seeing these tables. What did we use them for? That is a great way to study. Look at all these equations. This is every equation I've ever put on any of your exams. What are they used for? How much you use them on the exam? Ask these questions, and that will make you happy that you have reminded yourself of what all you've learned this year, because it has been significant. Happy studying.